Okay, so yesterday we finished talking about displacement and distance traveled, which was pretty easy. You just take final vector minus initial vector, there's your displacement vector. And then for distance traveled, we really just do the arc length. So now we're going to talk about a couple of things. One is breaking down the acceleration into tangential and normal components and writing out what those look like. And then we'll look at a physics application with some parametric equations and go through that. Yeah. So here's the theorem. If a particle moves along, let's say, a smooth curve C in 2 or 3 space, the usual, then at each point we can write the velocity, which we've already done, as speed times unit tangent vector. Okay, so that's from before. And then here's the new part. The acceleration vector can be written as second derivative with respect to t squared, and then times the unit tangent vector, plus curvature times ds dt squared times the unit normal vector. Well, here's what we're going to do. Okay, so here's what's going on.
Oh, because one thing is the tangential.
Right. So if we draw this in, maybe this is the unit tangent vector, which obviously is along the velocity vector, which could be larger or smaller, but that's one unit length. And then part of the acceleration, so I'll do those in green, we'll have a tangential component in the same direction, and that's what we mean by d squared s dt squared t. But we also have a normal component, so here's the unit normal vector, which points inward. Oh, I should have done that in red, sorry. And then the normal component of acceleration would be here, and that's the second part, curvature times ds dt squared times normal vector, unit normal vector. Okay, so if we're cruising along a curve in this direction, at any given point we have a tangential component of acceleration, this green one here, which is written as this, and we have a normal component of acceleration, which is written like that. Okay, now we're going to have some fairly simple ways to calculate some of the stuff, but ideally here's what you need to know. Okay, so acceleration is going to be written as a sub t times unit tangent vector plus a sub n times unit normal. Okay, so I'm kind of simplifying this notation here. Okay, we have tangential component and normal component. And just to make things clear, all right, this coefficient is the tangential scalar component of acceleration. And this would be the normal scalar component of acceleration. Okay, so they're going to really ask you to do two things. One is to find the scalar components of acceleration, and then also the vector components. So if we look at each part individually, this whole thing would be the tangential vector component. And then this whole thing, coefficient times unit normal, is the normal vector component. Okay, so here's what we really need to know. This, the way it's written currently, acceleration with all this stuff, with the second derivative with respect to arc of the arc length with respect to time, and then curvature times velocity squared, essentially, or speed squared rather. This gives us some insight as to like how the particle or object is moving along the curve and what's going on. But as far as computation is concerned, these are not, I mean, they're not horrible, but if we have arc length and we had to find an arc length parameter and we don't have that necessarily, so there's a lot of hoops we have to jump through if we want to calculate the scalar components and the vector components with these formulas. Okay, so the best way to do it is with these. Okay, so if we have that same curve, and maybe acceleration vector looks something like this, then what we can do is say, well, we know that there's going to be a tangential component, so that will be a sub t times unit tangent vector, and there's going to be a normal component, so that will be a sub n times unit normal, so that when you take these two green vectors and add them together, that's going to produce the final acceleration vector. Okay? Now, if we take the unit tangent vector component here and create an angle theta, that's with respect to the acceleration vector, then we can actually compute these pretty easily. And that will look something like this. So that scalar coefficient, okay, so if I'm just looking at the over length, that would be magnitude of A, I heard a couple of you say, times what? Cosine theta. Well, we're going to try to do something which is going to seem unusual, but will make things a little easier in just a minute. So does this part make sense, that scalar coefficient is going to be magnitude of acceleration times cosine? Okay? Well, I'm going to go ahead and bring in velocity. So magnitude of velocity times magnitude of acceleration cosine theta. But I can't just throw it in there without undoing that, right? That's why I did that. This formula now is simply the dot product of v dot a over magnitude v. Okay, so the tangential scalar component, this is a lot easier for us to calculate, isn't it? Because if we have a position function, we can find velocity vectors, we can find acceleration vectors, we can do their dot products. That's not a big deal. Okay? And if we do something similar with the normal coefficient, we're going to do that, yes. So that would be magnitude A sine theta. And the reason we're headed towards dot products and cross products is because that's how we relate vectors using cosine and sine, right? So what would I need to throw in here? to get the cross product? I still need magnitude v, just like before, sine theta, and if I put that in the numerator, I need that in the denominator. And now, this is, well, it's not exactly the cross product. What is this really? It's the magnitude of the cross product of v with a. Good. Over magnitude of v. So this would be a nice formula to compute the normal coefficient of that normal vector. That was the formula for the cross product magnitude. Remember that this also represented like the area of a parallelogram, so if you remember it that way, this makes more sense. Yes?
Okay, so acceleration is just the second derivative of position. Right?
Yes.
So what is this normal component of acceleration?
So at any given point, you have several things going on. You have direction of motion, which is entirely related to velocity, right? Whichever way the velocity vector is pointing, that's the way you're heading towards. But then there's also this acceleration vector, which is changing your velocity vector, right? So if we're looking at this curve over here and we're taking kind of a left turn, well, from our perspective, if we're going that way, that means there's an acceleration vector pulling the velocity vectors in that direction. Does that make sense?
Yeah.
And now for each of those vectors, just like with any vector, there's got to be a well, it's not exactly vertical and horizontal, but I mean, if you twist it and make it that perspective, there's always two components, a unit tangent, unit normal, but obviously they're not going to be one unit in each direction. It just depends on how big the acceleration vector is. So that's what we're looking at right now, is basically decomposing an acceleration vector and figuring out, well, in the tangent direction or in the velocity direction, how much is the acceleration in that direction and how much is actually pulling me in the other direction. Yes?
The normal and the tangential accelerations would equal, would that make a circle?
Yes. Absolutely. Yes.
So we would never have to do this to find acceleration, it would mostly be to find these components.
Yes. You would be explicitly asked, find the scalar and tangential components of the acceleration for this position function. And we'll do that.
If we need to find acceleration, we would just use like the other stuff.
Right. Find the derivative, find the second derivative. Yes, exactly. Okay. Now, this is sometimes going to be asked too, so I'll throw this in there. Sometimes they will ask for curvature. And now, here's a good time to review something from 12.5. What was the more convenient formula for curvature that we used? What was it?
DRDS.
So r prime crossed with r double prime cubed, wasn't it?
Yeah.
Okay, let's tie this into what we're doing here. So another way to write curvature in this context would be magnitude of, what's r prime really? V cross a over magnitude of v cubed. Okay, so one and the same, right? All right, so let's go through an example of what you'd be likely to see. Well, in anywhere. This is as extensive as we're going to get. So really, it's just a matter of knowing, hey, you can break up acceleration to point in the direction of motion and then in the other direction towards where I'm headed. And then here's what the coefficients or the magnitudes of those components are going to look like. Okay? Let's make sure I'm on the screen. Okay, so here's an example. Suppose, make sure I'm on the screen and I'm not on the screen at all. Awesome. Good job, Mr. Gonzalez. Okay. Suppose a particle moves along c, and c is defined by the vector valued function t squared, t cubed. Okay, so one thing you might be asked to do is to find the scalar, tangential, and scalar normal components of acceleration. Okay, so this is putting into effect what we just derived. Okay, so to find scalar component of the scalar tangential component, we're after a sub t. The normal one would be a sub n, right? So what do we need to do? So what would v be? And then acceleration would be? Good. So now we know that scalar tangential is just v dot a over magnitude v. So the dot product here would be 0 plus 4t plus 18t cubed over the magnitude of v. So that's the square root of 1 plus 4t squared plus 9t to the 4. Okay? So there's our tangential function. To find the normal scalar component, we want to do magnitude of v cross a over magnitude v. So we want to find the magnitude of some vector. Let's just do the cross product up here. Imagine I, j, k, right? Whatever you have to do. What's the first component going to be?
Six t
6t
squared.
squared. And then the middle component will be the opposite of 6t minus nothing, right? So negative 6t. And then the k component would just be 2 minus 0. So 2. And that's still over the magnitude of v, so that's still 1 plus 4t squared plus 9t to the 4, all in a square root. So if I find the magnitude of that, let's just put it in one big giant happy square root. That'll be 36t to the 4 plus 36t squared plus 4, all over 1 plus 4t squared plus 9t to the 4. Okay, so there's our normal scalar. Here's our tangential normal. That's the end of part A. Suppose you could clean this up a little bit, but that's fine. Second thing they could ask. Same thing, find the scalar, tangential, scalar normal components, but now they'll give you a specific value, like t equals 1. Let's just plug them in, yes. So let's do that. So when I plug, let me write it like this. A t of 1. Bless you. If I plug in 1, what do I get? 22 over square root of 14. Okay. Normal at 1. Would be what? root of 76 over 14. Okay. Done. C. Find vector tangential and normal components at t equals 1. Okay? So we need to find unit tangent vector, right? Because once I know the unit tangent vector, then I can multiply that scalar for the tangential with unit tangent vector, and that would be the answer. So in this context, we would write it as v, right? V of t over magnitude v, or v of 1, since we're actually plugging in 1, right? Over magnitude of v of 1. Well, we already have the denominator, that's root 14, right? What velocity vector do I get if I plug in 1? 1, 2, 3. Okay? So let me actually write it. I don't like it that way. You can write it that way, though. Okay, so there's the tangential vector. So, well, that's the unit tangent vector. I'm not quite done yet. The tangential vector, that's the whole thing, the scalar times unit tangent vector, right? And we want to evaluate this at 1. So we have a sub t already. It's 22 over root 14. And we have now the unit tangent vector. So if we clean that up, 22 over 14 is the same as 11 sevenths. That will be 22 sevenths and 33 sevenths. Okay? So this is your tangential vector component at 1, and this is your normal. Oh no, didn't do the normal yet. Sorry. This is the tangential vector at t equals 1. This is just the unit tangent. Okay. Now, there's a hard way to find the other component that we need, and there's an easy way. The hard way would be to go ahead and find the unit normal vector, and then take the unit normal vector times the coefficient that we have here. That is, yeah, I don't want to do that. If we go back to this, the whole point of this decomposition was that we can add these two vectors together to get acceleration, right? Well, can't I just solve for this algebraically? That's the easiest way to do it. Because I know I have this already. That's good to go. This is not hard to find. I could just plug in 1, right? And then you just subtract, and then you save 5 minutes of calculations, because we know how tedious finding normal vectors and unit normal vectors can be. All right? So the normal part, since we know acceleration is just a sub t times unit tangent plus a sub n times unit normal, I'll just say that my unit normal vector will be acceleration minus a sub t times unit tangent at t equals 1. Okay, so acceleration vector at t equals 1, it's somewhere on my work here. You guys probably have it somewhere. 0 to 6, it was 0 to 6t, so 0 to 6, right? And then we already calculated This one, it's right above. It was 11 sevenths, 22 sevenths, 33 sevenths. So then if we do the math, we are done. Negative 11 sevenths, 14 minus 22, negative 8 sevenths, 42 minus 33, 9 sevenths. So here is the unit normal vector, or I'm sorry, the normal component. They're so wordy. The normal component of acceleration, the vector anyway, and here's the tangent component of acceleration in vector form. Okay. I think we can forego the curvature example. You guys know how to find curvature. All right. In terms of what? If they give you an equation in terms of arc length, then it's not so hard to do the other formulas that we had. Yeah. Which is, yeah, so find ds dt, d squared s dt squared, and then you can still do the same thing as before. You don't want to do the normal part the long way. Just find the tangential first, plug in the value for acceleration and subtract. But typically you're going to have them in terms of a time parameter. Arsh.
So RT represents position function.
Yes, absolutely. Yep.
So would we ever have to like convert an R of S equation into an R of T equation?
No. If it's already in terms of arc length parameter, then you should just work with it in that format.
Okay.
But like I've said before, the purpose for us anyway with an arc length parameter is to provide insight as to what's going on, because we can interpret moving along a curve in respect to like how much distance we've traveled. And then later on down the road when we start doing multiple integrals and stuff like that, a lot of the interpretations using arc length make more sense to start than just going straight to the rectangular formats where you have a bunch of stuff that's in there but easy to work with, but it's kind of like, well, what am I really finding? You know what I mean?
Yeah.
So it's more of make sure you can parameterize something in terms of arc length and just know that that's going to help us when we figure out what we're doing later. Okay? But, I mean, we're getting ahead of ourselves there. Okay. So then there's one last thing. And it all comes from Newton's second law of motion. And if you are in physics, this should be piece of cake.
Physics on the test.
Well, that's what we're doing.
No, but like using our equations.
Use your equations.
Like v cosine v.
Well, that's pretty much what we're going to do. They're all the same things. Using, I always find it funny. Can we use that's the same. So yes, use quote unquote physics. It's just math. That's all it is. Newton's second law says force equals. Yes. There are some basic assumptions with this. Mass is constant. The only force acting on an object, so if we have something here, is gravity, right? Yes, above the ground. So maybe there's some object at an initial height. So let's label that S naught. Maybe there is some initial velocity. And the path of the object would then maybe look something like this. Okay. Using this model, since the only force acting on the object is the force due to gravity, we could say that the force is minus mg times j, since that's two-dimensional here. And if we plug in ma,
Why is it S?
why is it s?
For the data.
That's just I don't know. I don't know what the reason is.
So like, doesn't mean like arc length.
It's not arc length in this case. No.
Just maybe.
Yes, not arc length. Okay, so here's where we're at. If I solve for the acceleration, this should make sense. It's just minus g pointing towards the ground, right?
Can you say that down is negative or positive?
You can assign it so, yes. We're going to work with up is positive, down is negative here. So then, velocity, if I wanted to find it, knowing that this is acceleration, right, would be what? The integral of that, yes,
Your initial goal was C.
almost.
You have an initial goal. Is there, wait, V equals V1 plus AT.
We're getting there.
So,
So this is minus GTJ plus constant, right? And at t equals 0, our initial velocity is just v0. That's the assumption we're working with here. Okay? So that means that if I plug 0 into this, that c1 is really just initial velocity. Okay? You guys good so far?
wait, how much more is this?
How much? Well, there's a little bit. It's fast, but
No, like,
space-wise, probably a half page to 2/3.
would it
I write large on my
fit
stuff,
in
so.
this little box?
No.
Or-
Well, it depends how small you write. I don't know.
I could write pretty small.
Okay. So we have this.
Oh, yeah.
And now if I want to find position, we can find the integral of v of t.
Oh. That's where you get the other one from.
Yeah, so it's all the same. We get minus 1/2 gt squared j plus v0 t, because this is with respect to t, plus another constant vector, we'll call it c2. But what's r of 0 equal? S naught. So then that means that c2 is S naught. Which in this case would be, since we're up, it's S naught j. Okay, so now we have r of t equals, and if I group some stuff together, minus 1/2 gt squared plus S naught times j plus t times v naught.
Wait, can we go back to the velocity?
Which one?
Velocity.
Here?
You, like up there.
Here.
Yeah.
Yep.
When you said at t equals 0,
V of 0 is just v naught, initial velocity.
so can we rewrite that as, like, can we replace C1 with V1?
Yes, that's what we did. And the reason is because, I mean, the assumptions were that we had initial height, initial velocity. So when we are finding our constants, that's really what those are going to turn into. Yeah. Okay. So now, parametrically, here's our velocity vector. Let's say we have some angle alpha. This would be v naught cosine alpha. This would be v naught sine alpha, right? So we could say that v naught, so I'm kind of splitting up this v naught over here because I want to be able to combine everything into one happy equation with all the components written explicitly. So v naught would be v naught cosine alpha I plus v naught sine alpha j. And if I plug that back in, So now we get r of t will be minus 1/2 gt squared plus s naught times j plus t, and now I'm going to go ahead and write, instead of v naught, write it in vector form, so v naught cosine alpha I plus v naught sine alpha j. And again, the whole point of me doing that was so I can put all the i's and all the j's together. So the only I component would be v naught cosine alpha times t plus, and now everything else goes with my j component. So that would be s naught plus v naught sine alpha, and that's times t, minus the 1/2 gt squared, and that's all j, which is where all your happy physics equations come from. Change, or not change, but the x position at any given time. Looking at this position function, we have only one component affecting that, right? So what's x going to be? V naught cosine alpha, right? And then the y position would be s naught plus v naught sine alpha times t minus 1/2 gt squared. And I mean, these should be, yes, drop the t, thank you. These should be the same equations that you do in physics. Maybe different labeling, maybe you use thetas instead of alphas, but it's the same. Now, we already talked about this, but it's worth writing down. Velocity in the x direction is v naught cosine alpha, and velocity in the y direction, so if we go back, that's back to here. Velocity in the y direction, so we're using this for velocity and combining it with minus gt. So in the y direction, we would have v naught sine alpha, and then this first component, which has a j, minus gt. Okay, so these are the velocity equations at any given time. And now we are done with all the formulas that you need to know for the exam. The rest is pretty straightforward. Here's a quick example. Baseball is hit with initial speed of 80 feet per second at an angle of 30 degrees with respect to the horizontal, and initial height of 3 feet. So let's just go through the whole thing. What are some parametric equations for the trajectory of the ball? That's all it's asking, yep. So what would x be? No, we'll leave it in feet per second squared. Yeah. G would be what in feet? Okay. Our texts and in DiffyQ especially, we use feet for whatever reason. So 32. Okay, remember that. 32 feet per second squared, yeah. Okay, so what's x going to be? X was v naught, which is 80 cosine 30 degrees times t, right? So that's easy. Cosine of 30 is root 3 over 2, so divide that by 2 times t, right? So there's the x position. Y is initial height, 3, plus v, yep, 40t, minus 1/2 g, so 16t squared. So all we're doing is plug in the values they gave us, okay? Part B. How high does the ball get? So yeah, in calc, what do you do to find maximums? And if we're interested in height, all we care about is the y component, right? So we do dy dt, which is going to be 40 minus 32 times t. Set that equal to 0 to find out at what time. And time is going to be 40 over 32 divided by 8, 5 over 4, 1 1/4, yeah? Seconds. So now plug that into y. So y of 1.25, and I'll save us the time since we're going to run out here. We get 28 feet. Okay, a couple other things that I could ask you. How far does it travel horizontally? Set y equal to 0 to figure out when it hits the ground. Once you know the time, plug it into x, right? So 0 is going to be 3 plus 40t minus 16t squared. You guys know how to solve that, right? Let's just cut to the chase. T will be approximately 2.57 seconds. Plug into x, and we get 178.25 approximately. Well, they would give you where that is and what the height is, and you can figure out at what height. I know what you're talking about. You have to figure out what height the wall is and when at what time it reaches that height, and if it's before or after. Yeah.
How do you model a wall?
Well, hold on. Last question. What is the speed when it lands?
Oh, when it lands. Oh, well, you found the time.
We already know the time. T is approximately 2.57. What's speed?
Velocity,
Magnitude of velocity, right?
Then you could do like dx plus the v1.
Yep. So our velocity equation,
Or like v squared plus v.
You always go like just 2 decimal.
yeah, I mean it'll say on the exam. So velocity would be 40 root 3 if we're looking at x, and velocity for the y direction would be 40 minus 32 t. So that's what you're going to do here, square root of all that. But this is at what time? At 2.57, right? So plug in. I know I'm running out of time. And we get approximately 81.19 feet per second. Okay, I know I went over. Here's how I'll make it up to you. Tomorrow we'll go over homework. Friday will be a discussion day. I'll push the exam back to Tuesday.
Yes.
Well, okay, I'm gonna cry.
Yes.
What homework do you have for Friday?